Hello, everyone. Okay, so until others join, please let me know if you have questions. So one thing is, I have sent out an email for the paper presentation selection. Sorry for the delays, but hopefully we are still stick to, or like we stick to the timeline, because once you select the paper by Friday, I will try to respond either on the same day or on Saturday at most, to make sure we don't delay our timeline. Not sure if some of you already tried working with Lab 1, but if not, please do so, because it will take you some time, right? And you don't want to lose track of different labs, because the second lab is 2 weeks after the first lab, and things will start getting messy. Last time we finished cache basics, which is all what you need for lab 1. So I highly suggest you start doing that. And if you got questions, just email me, and we can arrange a time to talk together. Good. Did anyone try to start the lab?
Well, I looked at it. Yeah.
Yeah, looked at it means like you just went through the
Oh, yeah. I just went through
document.
what we have to do and then saw the
Okay.
questions. And yeah, I just needed to review the last lecture and then I'll attempt it this weekend.
Good. That's good. Yeah.
Also,
And okay, sorry. So I had a question actually about lab one, and the question about the recorded videos. So starting with lab one, so we are supposed to push our things into GitHub, like we will push a document, PDF document with our answers and at the code itself, right?
Correct.
Okay, so this is good. If we finish anything, like push it into GitHub, or like once we finished the whole lab,
It doesn't really matter. I mean, feel free to
I
push
mean,
as you wish,
okay,
but you'll only get graded after the deadline. So yeah.
okay, I see. Yeah, this is okay. The second thing, like we didn't have the links for the recorded videos yet.
Yeah, because I didn't promise that I'm going to do that, right? So what I said is I will
Okay, I see.
try. So to be honest, I didn't decide yet. But what and the other thing, I didn't have time, to be honest, to think about it and to
Okay,
process it and decide. But you have the detailed slides. So what in fact, what you need to know is all in the slides. But I understand also that lecture recordings might help as well, right? So
yeah, because there are some discussions. Like I remember, like there was a discussion about specific thing last lecture, and I wanted to look into it. For example, so it wasn't in details in the slides because
yeah,
it's just yeah. So
I would
something
say
like that.
generally, okay, good. Generally, don't depend on you will get the recordings.
Okay.
Like for example, if there's something, just take notes or write down something as usual if you do in any regular lecture, right? But that doesn't mean I'm not going to post the recordings. I was very busy with undergrad course problems, and I wanted to, I have some other deadlines that didn't give me a chance to process and upload the recordings. But until I do so, okay, the thing that I most likely I'm going to do is I'm going to post them, but I ask you that you only make them private, don't share with anyone else. Uh, but until I do that, don't depend that on the recordings, because it's also important to take notes while in the lecture. This will make you attentive. Sometimes knowing that you will have the recordings will make you a little bit less attentive during the lecture, right? Uh,
Okay.
uh, but as I said, most likely I'm going to post them maybe soon during this weekend. Um, yeah,
Okay. Yeah, I see. Okay. Thank you.
Excuse me, Professor.
yeah,
Can you hear me?
yeah.
Yeah, because sometimes, for example, we were looking back to the notes, and to review it, it's better to have your explanation on it, right? Because, for example, for set associativity, those things will appear on assignment. I was trying, and I sent you email about it, and without hear somebody to talk to explain, just looking at it, it takes a lot of time. Like it takes a lot of extra time, especially for me have very little foundations on it.
Yeah. So Sorry, again, I just have your username. Can you remind me of your email? Okay, sorry, of your name, because I want to call you with your name.
Oh, hold on. Let me change my name.
Yeah. You know,
I didn't notice that.
Change mine as well.
Yeah, I did. You can call me Jackson or
Jackson,
Hanji,
okay.
whatever.
Yeah. So Jackson, in fact, you are one of the reasons that I'm going to upload them, because I admire that you don't have the sufficient background, but you are willing to learn. And I believe the recordings will help you with that, right? But the problem, as I
it's
said,
gonna
I was
help
a
a
little
lot.
bit busy. Yeah, so I hopefully I'm going to do this week. But as I said, one thing, for example, is try as much as you can to put your explanations or notes during the lecture. If you got questions, feel free to ask, and this will help until we get the recordings, which hopefully this week should be the time to have some free time and sit and upload these. Okay.
Thank you so much.
Good. Thanks. Is there any other question?
I have one question.
Yeah.
Do we need to assume a certain format for the GitHub repository when we like upload the code and the document as a solution?
When you say format, what do you mean by format? Like file structure, for example?
Yeah, the folder structure template for the project or for the assignment.
Yeah, you only have the constraints that are mentioned in the PDF. For example, you write most of your code in a single file with the name that is given, these things. Other than this, if there are no constraints mentioned in the file, then you are free to use whatever structure you would like to do. Good?
Okay. Okay, thank you.
Okay, good. So is there any other question?
Yeah, last question related to the papers your selection. So I have already sent an email, but in the meantime, like I have an idea related, like I wanted to discuss with you, for example. So what should I do? Like, should I
when
just...
you say idea, you mean like another paper you want to present or an idea for the project?
Yes, exactly. No. Another paper I want to present.
So what you should have done is, with the email you sent, you might have mentioned that you have another paper that maybe it's better to discuss, and you give me the name of the paper. So what you can do now is just reply to the email that you sent to me with the paper, maybe a very brief explanation of the bigger picture of the paper and why you want to present it. I will give it a look. Maybe we have a discussion, and then we can decide. So as I said at the beginning, you are free to select papers other than the pool that I sent, but you need to let me know about this as soon as possible, such that we can discuss and see whether it fits or not, right? And this is a message for everyone else as well.
Okay,
Good?
I'll do that. Thank you.
Yeah, thanks.
Yeah, thank you.
Is there any other question? I guess you guys also saw my... Yeah, go ahead, Mr. Fikar. Yeah.
Oh, sorry. So you said you sent an email about the papers recently, but I didn't receive any emails. So maybe I'm not added to like a mailing list or something.
Yeah. It's. I'm not sure if I sent this before you, because I saw you on Avenue and I saw your email, but maybe.
Yeah.
Okay. So the email I sent, did you see my announcement on Avenue?
Yes, I did.
Okay. The email is exactly the announcement.
Okay.
So you don't need to worry. It's just saying I have already added the pool of papers there with the PDFs, and what you need to do is to select two reference. It's exactly the announcement, just copy and paste. Yeah.
Sounds good. Thank you.
Good. Thanks.
Okay, another thing. Sorry for this.
Yeah.
But I understand that we will write a paper like in IEEE.
This is for the project, Mohammed. This is not for
the
paper
project.
presentation.
Okay, yeah. Okay, sorry for that. Okay.
For the paper presentation, you are selecting a paper to present, right?
Okay, I see.
It's different than the project. Yeah. Is there any other question?
I did. Yes, yes. Thank you, Professor. I actually had a question regarding the project.
Yeah.
It's mentioning that the idea selection is due this Friday, and I'm just wondering in terms of, I know you made it completely open for us, but could you give us a type of example for the project?
Yeah,
that's to see maybe the amount of information we need, or
Good. That's an excellent question, John. So I guess also in the first lecture, what I said is you are free, for example, to send me an email that you want to discuss. So these kind of things, it's better to discuss individually to see, to stem a discussion. Everyone has his own expertise, his own field, and as I said, it's widely open. So maybe what you can do is send me an email, we arrange a time, 15, 20, 30 minutes, we discuss, and I will give you a feedback on whatever idea you would have. The only thing you need to do this Friday is only selecting the idea and talk to me, right? Nothing is like written required as far as I recall. So it's just a kind of a milestone for us to know we are in the right track. So what I advise to do is you just send me an email. We arrange a time to talk, to discuss if you have ideas. If you don't have ideas, I can give you suggestions. But I prefer to do this individually for each one, given his own expertise and whatever he would like to look on, right? Does this address your...
Perfect.
Yeah, perfect. Thanks.
Yep. Thank you very much.
Thanks. Okay, is there any other related question? So in fact, for the project, I was expecting to receive emails from you all. I'm talking about like all, not just John, like from you all during this week. And today is Wednesday, because you have to come up with an idea this Friday, or talk to me to give you some hints, right? But let's discuss as soon as possible. I'm free after the lecture as well if someone wants to discuss. But again, we might need to do this individually to for each one. So just send me email, and then today and tomorrow we can arrange a time to talk Friday as well. Hopefully by end of Friday or maybe Saturday, we all have ideas such that we can move to next milestones. Good. Is there any other question related to logistics?
Yes. Speaking of the project, actually, since I joined, I missed the first lecture because of the late joining thing. I actually, up until it was brought up, completely forgot about the project. So if you could upload like maybe the first lecture, so that if I watch it,
it's
and
already.
hear what
Oh, I see. Okay, but all the details.
Yeah, because
okay. Did you see the slides at least?
Yeah, I skimmed over it, but yeah, it just skipped my mind completely.
Sure. Yeah, that's okay. And you have an exception because I know you already joined late. So you might not be very restricted to the deadline this Friday, given that you were 1 week late anyway in the enrollment, and I know the situation. But that said, all the details of the project are already, in fact, in the slides of lecture 1. So, like the first lecture was had lecture 0, which is the big picture, and then lecture 1, which is discussing the cyber physical system introduction as well as the logistics. Please at least go through them, and then maybe we can talk and see how we can proceed.
Okay, sounds good.
Good, thanks. Okay, if there are any other questions, please feel free to ask, because I guess things are started scrambling, and then I would rather clarify any concern you have right now to make sure we are in the right track. Good. Okay, good. So we stopped here last time, and we started discussing DRAMs. After discussing caches, we said that we went through some of the examples where you have a row hit, row miss. So the first one, for example, you bring the row into the row buffer. The second request, you access the same row, so you don't need to activate or pre-charge. You just do the read write, and you have a row hit. And then in the second, which is like the third one, again, you access the same row in a different column, so you hit as well. But then finally, this is the bad luck situation. You access a row that is different than the one that is open in the row buffer. And in this case, you need first, this is called row conflict. You need first to pre-charge the original row back into the cells through a pre-charge operation. And then you need to bring in the new row, which is row 1. And then you do the access. So you need the full 3-step operation. And one of the things we mentioned last time is that this gives a huge variation of the access latency of DRAM, ranging from, for example, 10, 15 cycles for a hit, up to hundreds of cycles for a miss, which is like a big variation gap for DRAMs in general. So this is about the architecture operation of DRAM itself. What about the electronics, the DRAM chip, right? As we said, the DRAM generally have multiple banks. Usually it's 8 banks for DDR3, Starting DDR4, we had 16 banks, and we introduced what we call bank groups. The same observation holds also for new memories like HBM as well. For the bank, yes, you have multiple banks that operate in parallel, but in fact, they share the command address and data bus. So they are not fully in parallel, right? Because someone might imagine that given that you have different banks, they are completely separate and you access them completely and simultaneously in parallel, which is not correct. You still have some timing constraints that would cause delays among requests of different banks. Yeah. This, if you open any book in DRAM architecture, you find something as large as this. And let's kind of distill down the details of this figure, right? Here we have what we call memory arrays or banks. In fact, we have 8 of them. And then for the bank, for each bank, you have the row address buffer or decoder and the column address decoder. So just look into this and here, this example here. So this is the row decoder, this is the column decoder, and here we have multiples of these banks together. So this is exactly this part of this figure. And then the IO gating or sense amplifiers is the row buffer itself. Afterwards, if you look into, and this is the IO, so you don't need to care about the IO for now. It's just like some kind of amplifiers and impedance matching. This is the data bus, DQ0 to each one is 8 bits, so DQ0 to DQ7, and then some selection signals as well. Generally, as a chip, this is like this dotted line is the chip itself. You feed an address. This address, as we said in the very first time we talked about DRAM, is a multiplexed address mode. So you feed the address in a 2-stage. First, you feed the address A0 to A13 and the bank address A0 to A2, because here you have 3 bits for banks because there are 8 banks. And then you feed first through A0 to A13 the row address, and then in the second stage you feed the column address. And then in addition to this, you have also some kind of what we call control signals that determine the command you send into the DRAM chip. We said we have a pre-charge command, activate command, and read-write command. These are determined based on these signal bits. CS is the chip select, RAS and CAS are the row address strobe, column address strobe, and write enable that says whether you want to do a read or write. ODT is, you don't need to care about ODT for now, and these are the clock signals, right? Good. So this is from the electronic side for those that are working in digital design. Good. So we have multiple banks. So in some cases, for example, if you look into if you have a desktop and you are able to see your DRAM module, you might find that you have chips in your DIMM. This is called usually DIMM. And in your DIMM, you might find chips both in both faces of the DIMM, right? In this case, that means you have a multi-ranked DIMM or channel. What do you mean by multi-rank? Another level of parallelism in DRAM, as we said last time, is multiple banks. So assume, for example, I have 8 banks here. You can combine this into what you call a rank, and you can have multiple ranks. I guess we already mentioned this briefly last time. And you can have up to 8 ranks on your memory, and in fact, or even ranks can be combined into what we call channels. For example, in your desktop, you might already have a channel or a DIMM, but you might have a slot that you can add another DIMM in. I don't know if some of you already tried this. You can increase your memory by adding more channels, such that you increase your memory capacity, for example, from 8 gigs into 16 gigs into 32 gigs. Did anyone try this before? Like extending his memory, for example? Yeah, good.
Yeah.
Okay, perfect.
But is this memory chip or the different DIMM share the same bus? I mean, they're connecting similar to the banks.
Okay, that's an excellent question, Salah. So in the DRAM terminology, we have 2 types of what we call multi-channel memories. And in fact, it might be a little bit confusing because people in different textbooks and different papers mean different things based on what they mean. I would tell you what exists in your desktop and your laptop, and I will tell you what others might also think, right? What exists in laptop and desktop is you have a single memory controller, because the memory controller is on a chip. So in fact, the component that is responsible for issuing commands to the DRAM, we said DRAM is off a chip, which means it's in a different chip than the CPU, and they connect together through the motherboard interface. But the part of the system that is responsible for issuing DRAM commands and sending the address and the data bus is on a chip with the CPU, and it's called memory controller, right? This memory controller, when you extend your multiple, like you add another DIMM, for example, you don't touch the memory controller because even you don't have access to the CPU chip, right? So you add only more channels here. But given that you have a single memory controller, the channels, in fact, will be sharing the data bus, right? So they would still share the 64-bit, it's a general one, 64-bit data bus. So they are not completely independent, but most of the time, the data bus is not the one that is causing the bottleneck in the system. It's rather the delays because of the commands we discussed last time, the idleness in the DRAM. So it's okay to share the data bus as far as you can utilize it. So you can add more RAM and more channels. Channels operate completely independent, except that they share the data bus, right? And this is what people usually mean by multi-channel. And this is in fact the physical case in our laptops. But in other systems, you might be able to design, if you are the system designer, you might even be able to completely add different memory controllers connected to different channels, right? And in this case, they don't even share the data bus because everyone would have its own data bus and address bus, right? This is a memory controller, and channel 0, channel 1, and channel 2. To differentiate both, so the main difference is here you have multiple memory controllers and multiple channels. Here you have a single memory controller and different channels. To differentiate both, the correct terminology that people should use, and as I said, like maybe some of them confuse it, name this multi-channel, but name this multi-controller systems, right? Does this answer your question, Salah? Hello? Oh, I'm still here. Do you guys hear me?
Yeah, I hear you.
I hear you.
Salah got disconnected, I guess. Okay. Is there any question? Okay. So this is the for those who said they already changed the memory. This is how a DIMM looks like in your desktop or laptop. And in this DIMM, you have two faces. Each one of them you might have chips only in a single face, which means you have a single rank, or you might have it in both sides, which means you have a dual rank, right? Good. So we said that each of these steps might have a data bus of 8 bits, right? It's usually 8-bit or 16-bit wide, right? A single chip. But in your system, you have a 64-bit address bus and data bus, right? How do we combine? How do we end up having a total of 64-bit from the memory? You combine different chips together, usually 8 chips at a rank, which gives you a total of 64-bit. Good. What is the good advantage of combining multiple chips to compose a wider interface chip is that you have a high capacity DRAM. For example, in your, I don't know, 4 gigs, 8 gigs, 16 gigs memory, a single chip might be, for example, I don't know, like 256 megs, right? But then combining all of them will end up giving you whatever 4 to 32 gigs you get as a total system memory, right? So you deal with all these chips as a single entity, which is great.
Excuse me, Professor.
Yeah.
I have a pretty stupid question.
No, go ahead.
So, for example, let's say you have a 16-bit address and you can only dealing with like the data bus is 8 bits. Okay. So we know on the address the bits have like different functions, right? So how you can divide them into like 8 by 8 because they have
8 by 8. Okay. So let me make sure. Okay, let me clarify one thing that I believe will answer your question. If not, let me know. Okay.
Okay.
So there are 2 separate buses: the address one and the data one. The data one is the one that we are talking about here, which is it has an 8-bit or 16-bit wide. Let's say it's 8-bit.
It answers. It answers already. I got it.
Okay.
Got it.
Good. Thanks. Okay. So the good thing is now by combining multiple chips together, you have a higher capacity memory, right? So when you send an address, so maybe something that I wanted to add that might also clarify more is that the address bus, some of the bits will be chosen to select which chip you are accessing. So the chip select will be part of your address bits, right? Good. And then the other good thing about combining multiple chips into one channel or one DIMM is the thing that you said you have done before, which is adding more DIMMs, right? You make your memory controller flexible in the sense that you don't need to care about how the chips are underlying, or if you have a single DIMM or multiple DIMMs, you just deal with a 64-bit interface and that's it. So which allows flexibility. You don't need to change CPU and memory controller if you are adding more memory. The problem with having a 64-bit wide memory is in the other side, granularity, which means if you had a single chip of 8-bit, that means you can get a single 8-bit at a time, which means 1 byte, right? So if a processor needs a single byte, it will be much faster. But now, even if the CPU needs a single byte, I have a 64-bit wide interface, which means at a time, I will get at least 64 bits or 8 bytes. So even if you need a single byte, there is no such granularity because the minimum data you can get is the 8 bytes or the 64 bits. So you have a higher granularity that more than, in some cases, might be more than what you need, right? Good. Is there a question? Yeah, go ahead.
Can you hear me? Yeah. Yes. Okay. But the granularity, isn't that an advantage that you get more of the bytes at one shot?
That's
because
okay.
That improves like the spatial locality, right?
Great. That's an excellent question. So from the angle you mentioned, it's an advantage. That's correct, because you get more bytes, and likely, as you said, with locality, you are going to use this, right? But on the other hand, it prevents you from, because transferring 64 bits will take more time than transferring a single byte or 8 bits, right? And maybe in some cases, you don't need all of that. For example, if you have a very small system, you want to access single byte, then it might affect that if you have a scenario where you need a single byte, you always get 8 bytes, which means you will ignore or waste. This is called bandwidth utilization. You get more data than you need, which means you waste some of the data, right?
Right.
But okay. As you can imagine, the winning one right now in most systems is that, okay, I get more data most of the time, I'm going to use it anyway, given that my cache line size is 64. And this is the reason of what you said, Mushfikar, is that our system's based on the fact that most likely I'm needing this data anyway.
Right.
I'm not wasting it. Good.
Okay.
Okay, perfect. Here, adding multiple DIMMs together.
Sorry, Doctor.
Go ahead, Mom.
Went down on the campus, so I and Salah wouldn't be able to enter the lecture again because the power is down. So I'm on my mobile now, and I'm not sure how Salah will handle it.
Oh, so what you are saying is that the connection in the campus is down?
All the power, yeah, the connection.
All the power, I see. Okay, so one thing is, in fact, you can join by phone, not on data.
Yeah, I did that.
But, yeah.
I did that on my data. So I'm not sure if Salah will be able to do that or not.
Okay, okay. I see. Okay, so this is one additional reason that maybe having recorded lectures would be useful.
Yeah.
Okay. Okay, so this is what I was explaining about 2 independent channels versus having 2 channels and a single controller. This is we already discussed, which is good. Again, this is a general memory structure. Like you have a channel that consists of multiple ranks, and then a rank have multiple banks, and the bank would have columns and rows. So we already went through this. This is the levels of parallelism in memory in general. A cell would be a single bit. Then you have rows and columns that construct a bank, and then a bank with a chip, multiple chips would give you ranks, and ranks together would construct a DIMM which has a channel, right? Okay, and this is the example that we're discussing about your own systems where you have a processor that can have multiple memory channels. Each one of them can be a DIMM. Perfect.
Just a question.
Yeah.
What does having two ranks, because you said if you have chips on both faces, then you have
Correct.
two rank. What does having an extra rank help?
Yeah, that's an excellent question, Mr. Fikr. So because you can think of ranks as a higher level of parallelism than banks. We said you can access banks in parallel, but you still have dependency, correct? We will see now in the lecture, once we go forward, accessing two different ranks even have more parallelism than accessing two banks in the same rank, right? So adding an extra rank will help you, in fact, increase the throughput because one rank is almost independent of the other one, right?
Right. So you're not always waiting for like one to be done before requesting for
Exactly.
the other bank. If you put it right, okay.
Correct.
Right.
Yeah. Okay. Good. 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 We already discussed this, and this as well. This is also how a bank looks like. It's just a different view of it. Here is one thing that is good to understand. Assume, for example, I want to transfer a 64-byte cache line. What would happen, right? In most cases, those 64 cache blocks, if they miss in a cache and they go to the memory, they will be mapped, for example, to a certain rank. But to increase parallelism, they will be interleaved across different banks on the same rank and different chips, such that you can access, because we said each chip is 8 bits or 1 byte. I want to get 64 bytes. So the right thing to do is to get a byte from each chip in parallel, and this will add up to be 64 bytes at the end, correct? Sorry, it would add up being 8 bytes because each one is a single byte, but then you do get this for across different cycles to get the whole 64 bytes, as we will see now, right? Which means at a single cycle in DRAM, you get 8 bytes, but because it's DDR, which means it's double data rate, so you get, in fact, data on the positive edge and in the negative edge of the clock. So in one cycle, you get 16 bytes, not 8, and that means you need 4 cycles to get 64 bytes. A bit of a detail that we will visit later in more explanation. But the general idea here is that you distribute or interleave a cache block across different chips to increase parallelism. Good. Here to illustrate this is, for example, I need the 64 byte cache line size. As we said, our data bus is 64 bit, which means 8 byte. Here a byte, a byte, a byte, and you increase this. This is how a cache line size is distributed across those chips. You get an 8 byte in a cycle, and then in another cycle, you get another 8 byte, etc., until you get the full 64 bytes. Good. Perfect. So now we have been linked.
So I have a question.
Go ahead, Mohammed.
So we need like 8 clock cycles to complete a cache line from 8 banks, correct?
Yeah, not 8. In fact, there are 4, and the reason for this is
positive and negative. Yeah, the positive
exactly
and negative, right?
Correct.
Okay. Yeah, I see. Okay.
Yeah. So now, how the DRAM latency, in fact, why DRAM? We said it ranges from, I don't know, like 10 cycles to 100 cycles. Why it takes that too much latency to get a request from the off-chip memory? For different reasons, right? The first one is, as we said, CPU is on a different chip as the main memory, which means you need first to give the control to the memory controller to issue requests to the memory that are missed in the cache, and you suffer from queuing and scheduling delays across the controller because, for example, if you have a multi-core, all the cores are trying to access this off-chip memory at a time, and you have queues that buffer these requests. And then at the end, the memory need to be, like those requests need to be translated into what we call low-level DRAM commands, like the ones we discussed last time, as like an activate, pre-charge, activate, read and write. And then you go inside the DRAM itself, you suffer from a bank latency, a rank latency, channel latency, and then you transfer your bytes back. You get the data on the data bus, the controller receives them, and then sends them back to the CPU. So it's a complete trip from the CPU to the DRAM and the DRAM to the CPU. We already mentioned that bank parallelism is good for achieving concurrent DRAM accesses because you don't need to wait for a bank to finish before you access another bank. And if you have ranks and channels, you add more parallelism as well. Good. So this. Okay, yeah. One example here is how multiple banks work, how they can do the overlapping or the parallelism, right? Assume I'm accessing different rows in the same bank. Good, which means you have a row conflict, which we discussed at the beginning of this lecture. In this case, you activate A here is the activate command. Good, which means just to remind you, you bring the row from the cells into the row buffer through an act, right? And then you need to wait for some time. In modern DRAMs, this takes something around 50 to 60 cycles before being able to activate another row, right? And you wait for the original access, and then you activate the second one, then you wait for that, and then you activate the third one. So 3 requests would be serialized, right? No parallelism at all if you have row conflict to the same bank. On the other hand, if I'm accessing different banks, those requests will be mapped to different banks. Each bank has its own row buffer, which means there is no conflict, and you can overlap. Here, you see the overlap of data transfers, right? So you finish much earlier through increasing parallelism. Is there a question here? Okay, Salah is back, I guess. Salah, are you back? Okay. Good. So address mapping. So understanding this parallelism would take us to how, and this is something related to assignment 2, in fact, because you would require to play around with the address mapping. So what is address mapping? We said that the DRAM would be composed of channels, and then this is assume this channel 0, channel 1. Inside channels you have ranks, rank 0, rank 1, and inside ranks you have banks, and inside banks you have columns and rows, right? So you have multiple levels of things. But we have, as a CPU, I don't need to care about all of that. What I need to care about is I send a memory request that has an address and a type, whether it's read or write. If it's a write, I send the data to be written to the memory. If it's read, I will be waiting for the data, correct? How using this address, and this is the main rule of having a memory controller, in fact, is that the CPU doesn't need to care about how the DRAM works. You just send your load and store instructions with the addresses. And then the controller will take this address, and based on this, it will do some decoding to determine what is the targeted channel, targeted rank, targeted bank, targeted column, and row, right? So you divide your address mapping in an operation that is very similar to, if you remember from caches, you have a set, index, and the tag. It's exactly the same thing. So you divide your address mapping into segments, what we call a column, a row, bank, rank, and channel, right? For example, if I have a 32-bit, I would say, okay, how many columns you have. If you have, for example, 1024, that means you need 10 bits for your column. And then if you have 8 banks, similar to what we discussed, that means you need 3 bits. If you have 2 ranks, you need a single bit. If you have, I don't know, like 4 channels, you need 2 bits, something like that, right? And for every address that is coming to the DRAM, the controller will take this address, do the decoding, determine which channel, rank, bank, and then target or map your request to the targeted channel, rank, bank. Is there a question?
Hello, can you hear
Salah,
me?
you are back. Yeah, we hear you now.
Okay.
Okay, good. Thanks. I guess, Salah, you had a question. Did you hear my answer for that question, or you got dropped out before you hear that?
No, I didn't hear.
Okay, do you remember the question?
Yeah, it was about using different DRAMs on the same bus. Is it like, is different DRAM chip or module or channel
I see.
share the same bus?
Now I remember. Okay, so maybe this is something that we can discuss on the break in order not to break the flow of the lecture, and then we can revisit on the break. Okay, thanks.
Okay.
Do you guys have any other question in that? Let me see the chat. Salah, okay, power outage. Okay, good. So we can have different address mappings based on whatever channels we have, right? Like, given that you have a 32-bit, I can map my address the way I would like. For example, I can say, I can put my channel, if I have, for example, 2 channels, I can put my channel bits at the end, or I can put them here, or I can put them here. Can someone guide me of why, for example, or what might be the effect of having different address mappings? How this can affect anything in the DRAM operation if I have the channel bit here, or I have it here or here?
The address decoder?
Yeah, like, yes, the address decoder will, yeah, for sure it will be affected because it will select which channel you access. But my main point is how the operation of the DRAM itself, like how this might affect, for example, performance or throughput or latency or anything. Is there an idea?
Is this like information sent serial or at the same time, like?
The address mapping is sent at once, right? So you just get it once. So it's just parallel. You get the 64-bit or 32 bits at once.
Okay, so I don't think it will affect the latency because we get all the information.
Yeah,
about
it
the
will not
address
affect the
one at a
latency
time.
of the calculation or the decoding, right? But let's say, for example, okay, let's say I have a sequence of requests, right? Maybe I'm accessing an array, for example, right? And the arrays are adjacent, array elements are adjacent in memory, right? Correct? And I assume each element of this are like, I don't know, it's an int, so it's 4 byte, for example. So if all those requests are adjacent in memory, but I have my address mapping such that my channel bit is towards the end, all of these will be mapped. Do you think all of these will be mapped to different channels or the same channel if my channel bit is towards the most significant bit?
Okay, yeah, it will be the same channel.
The same channel, right? Because the change here, for example, if this is address 0, this will be address 4, 8. So you look into the binary, only the least significant bits will change. The last bits will not change, correct? So adjacent requests will be mapped to the same channel. So in fact, you didn't utilize much the parallelism you would like to utilize, right? On the other hand, if you place the channel bit somewhere in the least significant bits here, what would happen? You start having some requests mapped to different channels, and you have interleaving, correct?
Yes, yes.
So the address mapping is one of the very important operations of the memory controller that determine the performance of the DRAM. Because the same observation we discussed about channels also applies for banks, right? And ranks. Because if your bank bits are towards the end, most of your subsequent requests will be to the same bank, correct? Which means if you have conflicts, this will be very terrible. But on the other hand, if you have locality, this will be good. So it depends on the patterns you would have. Most of the modern machines, in fact, some work I was doing with the Intel memory controllers, I was trying to reverse engineer their address map. These things are proprietary information, so they're not publicly available for Intel or ARM or etc. But what we discovered is they have the channel, for example, the channel bit is bit number 6. And the bank bits are somewhere like 5, 4, and 7. And the rank bits are also in the least significant. So most of the interleaving bits are towards the least significant bits. And the reason for this is clear, what we were discussing right now, which is increase interleaving and parallelism to increase throughput, correct? Does this make sense?
Yes. So basically the channel position define how much the data is interleaved in different channels.
And the same thing for rank, the same thing for bank. That's correct.
Okay, but I don't see what is the benefit to have the data in different channels. Is it like because we can access it in parallel or?
Correct. Like increasing, for example, if 2 requests are mapped to the same channel, they have completely different timing constraints than if they are mapped to the same rank or same bank. I guess I'm not sure if you were here when we had this example, but what we were saying is that we just to illustrate the parallelism, the first sequence of 3 requests are being mapped to the same bank, which means you need to wait for every request to finish before issuing the second one. So they are serialized. On the other hand, if they access different banks, you can access different banks in parallel and you start overlapping the data transfers. So it will make things much faster. Good. And
Yeah,
the same thing
absolutely.
applies for ranks, the same thing applying for channels. Good. Is there any other question? Okay. Yeah. So one way that the DRAM is interacting with the operating system is that, in fact, the system component, if you remember our very first lecture, lecture 0, when we had the full stack and we had the operating system, application, and then ISA, and then architecture, this is one way that the hardware is talking to the software and the software is talking to the hardware, because CPUs usually, or applications running in your laptop or desktop, generally they don't send memory requests in the address of the DRAM. DRAM is usually called this physical address, right? But most, I don't know if you hear about this, but most likely in one of the undergrad courses you heard about virtual memory, right? Where processes are generating requests in a virtual address that is not the actual address where data resides in memory, for security reasons and other reasons, right? One of the functions of an operating system is to do the translation from virtual to physical addresses. This is called the virtual to physical mapping, and it's done at the operating system with the help of a memory management unit. So for example, if you have a virtual, so this is your virtual address that is being generated by the CPU. And then the operating system is doing the mapping. Some of the solutions, for example, that exist in industry and academia is to try to play a bit with this operating system mapping, such that you select how to map the banks and rows and columns for different architectures. I will give you one simple example, and we will revisit this example when we talk about predictable architectures. For example, if I want to make an isolation between cores, assume you have a multi-core architecture, and all these cores are competing to access the DRAM, and the DRAM is composed of multiple banks, right? We said bank parallelism is great because they increase throughput. But what if you have a predictable system, for example, in automotive, and you want to secure or save the critical task from the interference of the non-critical task? What you would do? One very simple solution is to say, if this is my critical core, or my critical ECU in the car or whatever, I'm going to map it to certain banks that no one else is going to access. But how to do this if you don't have access to the hardware? Does anyone have any clue from what we are discussing right now? Yeah.
Yeah, from the virtual mapping is allocation of the address bit. We can assign a certain bank for the critical.
Exactly. Something to play around with on the operating system is to say, okay, this is a software function which I can control to say, for example, if this is core 0, all the requests will be mapped to bank 000, which means after you do the mapping, you just mask these bits. So this is called bank partitioning. So you partition the banks among cores using only operating system solutions. Is there any question about that? We will discuss in some detail, because this is one of the most common solutions in existing in safety critical systems like automotive, avionics, etc. We will revisit it when we talk about predictable architectures. But this is just one example of how you can leverage the interaction between software and hardware to achieve a certain task. Good. Okay. Great. Another thing that we touched very briefly in the last lecture is the DRAM refresh. We said that a DRAM cell is composed of a capacitor and a transistor, and this capacitor, because it just holds charge, you need to periodically refresh it such that it doesn't lose data. It doesn't, like the charge is not leaked, right? And refresh is a periodic task in DRAM that happens every 64 milliseconds. And it's one source of the delays of how DRAM is not very efficient, because once you start refreshing a bank, it blocks all the accesses to that bank, right? Which means it causes more delays to memory requests. Yeah, this is what we discussed. Okay, there are two modes of doing refreshes in DRAM. One of them is what we call burst refresh, which is, okay, you have multiple banks. I'm going to refresh all of them together in parallel. What is the advantage of this? The advantage of this is you make the access to the DRAM. So for example, you do something like this. This is your refresh period. And during this time, you refresh all the banks. So you free the banks during the normal operation time. But the disadvantage is during this refresh, because you refresh all the banks simultaneously, you take more time. So during this time, the DRAM is completely blocked, right? So that's good for throughput because in general, like the DRAM is available most of the time, but it's bad for latency because one simple example, if a request arrives directly before the start of the refresh operation, what would happen? It has to wait for all the refresh to finish, right? This is called burst refresh because you do all the refreshes in burst mode. On the other hand, there is another possibility, which is doing a refresh in a distributed mode. So for example, say, I'm not going to refresh all the banks simultaneously. I'm going to distribute my refresh across the banks over the time. What is the good thing of that? The good thing of that is now the latency suffered because of a refresh is much smaller. But on the other hand, you make the like the DRAM sometimes is not available. So the available time here is much more larger than the available time here because this is being kind of interrupted by the going on refreshes. So it's a throughput versus latency trade-off, right? Is there a question? To give you like a simplification of this scenario is something, for example, like you are going to buy a car and it's going to cost you like 50K. You either pay the full 50K at once, and it's like a burst mode. So you take the hit and you are done. Or you say, I'm going to finance this, and then maybe every month I pay like 2K, 3K. But that means it's a recurrent, like recurrent cost, right? This is the main difference between burst refresh and distributed refresh. For some, burst would be great because you pay it and you don't need to care afterwards. For some, you cannot afford the latency of this large refresh or the cost of the 60K or 50K, and then you say it's better for me to finance them over time. Is that clear? Okay, this is exactly what is being discussed here. So the first one is
Dr. Muhammad,
yeah, go ahead.
I have a question related to the previous slide.
Yeah.
So if I have like random axes and linear axes, for example, so from this, like the random axes will be good with the distributed refreshes, right? And
why?
the axes, because like I distribute the refreshes of the rows or the banks across the period of the refresh time, right or not? Because I was thinking about it. So will like one of these terminology will be better for the linear axes rather than the other one or not?
It doesn't have a direct relationship, right? For example,
Okay.
assume you have a random sequence of axes, right?
Okay.
Then if you do the burst refresh, you will still need to pay the full price of the refresh. So a request latency would still be huge. On the other hand, if you do the distributed one, then the latency would be less. That's correct. But your throughput will be also less. So you decrease throughput because every while and then you're going to pay the price of a refresh. The same thing applies for the sequential access pattern, right? Maybe one possible advantage of having the burst refresh for the sequential accesses is because in the burst case, for each refresh, you are going to close the bank, the row of that bank, right? So
Okay.
if you distribute this each time, you're going to close the row, which means if you have sequential access that have a lot of row hits, your row hits will be closed here and you have to reopen the row after that, right? But here,
I see.
the row will, okay, you close it here, but once you open it here, it will remain open for a long time. So sequential accesses will leverage the open or will enjoy the open row much longer if you do have a burst refresh. But you still, if you arrive here, you are going to pay the full price of the worst case latency.
Okay, I see. Okay.
Yeah, thanks.
I have also a question.
Go ahead, Sam.
Yeah, about the time it take to refresh the banks
Yeah.
on both the distributed and burst. Is it like the same time? I mean, I know that it's different in time, but on overall, when we look at a certain period, is it like the same amount of time?
Yeah. If you sum these things up, I believe this is your question. If you sum these things up over a period, all these boxes, they will give you exactly the same number of boxes here. So the need, like the total latency you suffer is the same. So the cost is the same. It's like saying if you do finance, there is no interest, right? It's the same price whether you pay cash or you pay by finance, right? It's just a matter of distributing it over time. Yeah.
Does that mean that the bandwidth utilization or the bandwidth will be the same? The access bandwidth for the memory should be the same, and I don't know why.
Yeah, that's a good question. An excellent one. Okay, theoretically you are correct. The ideal bandwidth is not affected because you still have the same number of free. So in the visual terminology, these spaces, if you add them up, they should give you exactly this space. This is what you are saying, correct?
Yes.
Yeah, yes. That's the theoretical bandwidth, right? But we said that DRAM would in fact have its own idleness because of the timing constraints, right? One example that I was just discussing with Mohammed right now, assume you have a sequence of sequential accesses, correct? They all target the same open row, right? During this time, each request, as we said before, might take something around 10 cycles, right? So if this time, for example, is 1,000 cycle, how many requests you can service? It's 1,000 over 10, so it gives you 100 requests, correct? On the other hand,
yes,
given that each refresh is going to close the row, each request that comes in after here is going to have a row conflict. So it takes, instead of 10 cycles, it's going to take, let's say, 50 cycles, right? Which means even if you still have the same 1,000 cycles theoretically, each request now takes 50 cycles, which means you divided this by 5. So you service only 20 requests. If each request is 64 byte, you can imagine that here we transferred much less. So in fact, you reduce the effective bandwidth by 5, right? By 5x. So the theoretical bandwidth remains the same, right? Which is how many bytes you can transfer. But because of the timing constraints of the DRAM, the effective bandwidth gets reduced heavily because that the refreshes are closing the rows and causing conflicts, right? Does this address your?
Yes, but also in burst refresh, we close the rows, right?
Yes, but
so why is the request take 10 cycles in burst
perfect,
mode? Is it
great.
because like
because
at
once
the
you
at the beginning?
because once the first one here would hit the conflict row, you are correct. But because we don't have any refreshes here, the row would remain open, right? Salah, did you get disconnected?
Okay.
Oh, you are still here? Okay, did you get that or?
Yes.
Okay, thanks.
That's why I believe, sorry, Dr. Wood, that's why I believe like the distributed refresh will leverage random accesses while burst refresh will leverage sequential accesses. I still see it in this way, as you clarified actually.
I gave the example of the sequential access because it's clear, but for the random one, I'm not sure because maybe it's indirectly. I cannot make a direct conclusion, to be honest, right? It might need to sit down and think about it or run some experiments to see if you have a random access pattern, whether distributed will be better than burst, right? So it's, I don't see a direct, it's not like the sequential, it's not a clear win for me, right?
Okay, I see.
Okay, so yeah, we already, excuse me. Excuse me. Okay, so we already discussed the refreshes. Excuse me. We already discussed also these emerging technologies for memories. So that's okay. Okay, here we come into some of the memory controller functions, which I believe will be very useful now. Forget about this for now. Here, how does a memory controller looks like? We saw this at the very beginning, but now let's look into this in some detail. This is a memory controller that we said is on a chip with the CPU. Different requests come from different cores into the memory controller. This comes at the, like in the format of a load store instruction and some address. The controller takes this, arbitrates means select which request you should service now, map them to bank queues based on the address mapping. For example, if a request goes to bank 0, it goes here. If a request goes to bank 2, it goes here after the address translation. And then you need also to generate. So this is the request that is coming to you. But the DRAM does not understand load store. It understands act, bre, read, write, its own low-level commands, right? So you need to do command generation and command scheduling. So after you translate the address and you translate the request into its own commands, now you would have a command buffer that should select, based on the timing constraints of the standard, which command is valid to be issued now, right? For example, if you know that you have a row conflict, you know that the valid command should be act first, or maybe a pre-charge if you need to pre-charge, and then an act, and then a read or write. You cannot just directly send the read or write. This will be invalid command in DRAM according to the standard, right? So these are the main 3 functions of a memory controller: is arbitrate among different requests, do the address translation from this format of address into the bank, rank, row, column segments that we were talking about, and then do the command generation to access the low-level DRAM details. Good. So looking into more about these queue sizes is, if you, this is another you can say another cross-sectional view of the memory controller. You have different requests that are coming from caches, which are like maybe the last level caches of different cores. They go to the bank queues as we discussed in the previous slide, and then you generate their own commands after the translation, and then you do some scheduling to select which command should be issued right now to which bank. And then finally, and this is what we meant by banks are not completely independent. If you have 2 banks that each one of them can take a command, you need to pick one of them according to the standard constraints, as we will see right now. And then finally, you pick a single command to be issued to the memory along with its targeted bank, rank, column, channel, row, for example, right? And this would be, for example, it's an act, right? And this will go to the DRAM. So here, this is a direction towards the DRAM device itself. And here, this is the interface with multiple CPUs, right? Is there a question here? Okay. So some of the scheduling things. So we said here, you need to schedule requests. You need, if you have multiple pending requests, which one to pick, right? The most naive one is you just do first come, first serve. When you get a request, you service the oldest one, right? This might be good in terms of fairness because the oldest one waited more and it has to be issued. But this does not leverage the different operations of DRAM. What do I mean? Assume that your oldest request, I'll give you an example. Assume that we have these 3 requests. So it's row 1, bank 0. And then you have row 2, bank 0, and then row 1, bank 0. This is request 1, request 2, request 3. And here we are talking about this is the oldest. So this direction is the oldest. So this is the head of the queue. If you do first come, first serve, can you imagine what's going to happen? The first one will bring the row in the row buffer. So you do an act command. You wait for some time to bring the row, and then you do your read, for example. Assume that everything is a read, correct? And then if you serve things in order, you need to issue the second request. The second request is a row conflict, right? Because it targets a different row in the same bank. So you need to wait for a very long time because of the conflict before you pre-charge. So you need to do the following sequence. Maybe I should move these here for readability. So the first access would be, I do an act, I wait for some time, do the read, and then after a long time between the conflicts, I can issue, this is act 1. Here I can do the pre-charge, and then the act 2. And then after I'm done with this, I will repeat the same operation because it happens that request 3 is in fact for a different bank, which is row 1. Sorry, the same bank, different row. So you need to wait for some time and then do the pre-charge, correct? So I wasted it. I need to show you the full diagram to make sure the idea is clear. So you have Act 1 here. After some time, you do pre-charge, and then you do Act 2. After some time, you do pre-charge, and then you do Act 3. If that's not clear, please ask, because that's very important. Why did we do 2 pre-charges here? Because the second request is targeting a different row than the previous one. This is why you need to pre-charge the old row first, because before bringing the new row. And then the third one is also targeting different row than the previous one, so you need another pre-charge. Is there a better way? Can someone think of a different scheduling that can help us? What do you think?
Request 1 and 3.
Yeah, reorder, right? Do some reordering. If I bring request 3 before request 2, service them out of order, the sequence would be row 1, and then row 2, which means the first one remains the same. But for the second one, which is request 3 right now, I don't need to do any pre-charge because it's targeting the same row, which means, in fact, I don't even need an act because the row is already available in the row buffer. And directly you do the read-write operation, right? So you do the read 1 and then read 2, which takes much less latency. And then now you need a single pre-charge after you finish request 3. This should be read 3. And then you need a pre-charge for the second request, and then you do the act of it for the second request, and you are done, right? So you did, so previously this was a miss, right? But if you do the reordering, this will end up being a mess, this will be a hit, and this will be a miss. So now, by bringing this here, so now you have more hits. You increased your row hit ratio. Is there a question?
Yes, I have a question here. So these requests are from the same CPU or different CPUs?
Does it matter?
Because I was thinking if for example, the requests that's like using row 1 will come from CPU 0, for example, and requests will come from for row 2 will come from CPU 1. Okay.
Okay.
Now if CPU 0 will issue like more requests for row 1, like bigger number than CPU 1, so CPU 1 will be delayed.
Correct. Correct. That's an excellent point. First ready, first come, first serve target is to increase DRAM throughput and minimize its access time. But it's unfair across cores, which means if there is a core that has more hits, it will in fact affect the delay and the latency of the other core. And this will become a huge issue when we talk about predictable architectures, right? Because now this maximizes the interference across cores, which is too bad. Think, for example, for the automotive scenario we given in the previous lectures, which is assume in the same system on a chip, your, I don't know, cruise control is accessing the memory, and the same time your infotainment unit is accessing also the same memory. And the infotainment unit, because it's like has a huge bandwidth, because for example, you are streaming something, whether audio or video, they have high locality, and which means they might saturate the DRAM by accessing the same row multiple times. This will affect the latency of your cruise control, and you don't want this to happen. So you need to decouple the performance of the cruise control from the performance of the infotainment unit. So first ready, first come, first serve is good for average case, but it's a typical case that is too bad for worst case. Good. And we will discuss this more when we talk about the DRAM for predictable architectures. But yeah, thanks, Mohammed. That's a good point. Is there any other question?
Yeah, but for this scenario that Mohammed just said, does the CPU still have a constraint about how many number of pending requests? So it cannot like issue any numbers of DRAM requests to the same row, or?
Yeah, it will be bounded by how many, by the maximum of possible pending requests in your out of order pipeline, right? When we talk about pipelining, we will see that if you have out of order core, for example, you are allowed to issue a maximum of 4 requests or 8 requests, right? And all of them can be to the same row. So you are correct in the sense that you still have a bound, which is the maximum possible bending requests for you, right?
Yeah.
I guess this is what you're saying. So yes, but that's still a big bound if you wish. Yeah.
Okay.
Yeah. Thanks. So guys, let me stop here and ask: does someone think that this is too complex, or you feel completely lost, or it's still manageable so far?
I'm actually not bad.
Okay, good, Jackson. Thank you. What about others?
I'm good.
Okay, good. Thanks.
I'm good as well.
Yeah, perfect. Thanks. Okay, this is just describing generally how you do scheduling. For example, we did prioritization based on request age, which is first come, first serve. But you also have the row buffer hit status, which is first ready, first come, first serve, the one that we did the reordering for. You can also do based on request types, like you schedule reads and writes differently. For example, if you have a miss or a load miss, restore miss, this is another thing. Request criticality is one thing that we will discuss deeply in the predictable architectures for embedded systems and cyber physical systems. Because, for example, in the scenario that I gave, you want always to give a high priority for your cruise control or your critical task over the non-critical task. Is that correct? Generally, yes, right? Because the critical task is very important. It has a very latency sensitivity nature, while the non-critical one is okay to wait for some time as far as the throughput is acceptable, right? And we will see this later. Okay, good. Row buffer management policy. So we said in DRAM, and I guess someone asked the question last lecture, and we briefly discussed that. So far, we are assuming that once you bring a request to the row buffer, you keep it open there such that if you have hits in the future, it will help increasing the throughput, right? But one way of removing this unfairness that we discussed about first read, first come, first serve, and improve the predictability of the system or the fairness of the system is to say, you know what, I'm not going to allow any hits to any row. What I'm going to do is each time I get access, I'm going to close the row after I finish my access. Close the row means do a pre-charge, which means always your row buffer will be empty. It's like saying you bypass the row buffer cache, no hits at all are allowed to the row buffer. Everything has to be brought from the DRAM cells. This will increase latency of a single request, that's correct. But as you can see, this will prevent any reordering and it will allow fairness for requests, right? I guess last time we discussed this by saying, okay, I will give you the example I said last time. As we said, if you have the open row policy, this is called open row policy, the one that you allow the row to be open in your row buffer. We said, if you have a hit, this might take, under open row, you might take something around 10 cycles. But on the other hand, if you have a conflict, you might consume up to 100 cycles, right? On the other hand, if you use closed page policy, which means each time you close the row buffer after the access, there are no hits at all, which is too bad. But also, in fact, there are no conflicts at all because nothing is there in the row buffer, which means you don't need a pre-charge at the beginning of a request. And you get something in the middle, which is, this is called closed row. It's not a conflict, it's not a hit. And you have something in the range of, I don't know, like 20 to 40 cycles. So it's like a middle ground, right? Is that clear? So open row policy and closed row policy have their own good and bad advantage. Like for open row, the advantage is if you leverage hits a lot, that's perfect because you increase your throughput. But if you have a lot of conflicts, it's going to be too bad. On the other hand, closed row, if you have a lot of hits, it will be too bad because now you don't allow hits. But on the other hand, if you have many conflicts, they save you the time and they reduce your latency. Can someone give me a possible pattern of like a program that will be better if we use open page? what would be the possible sequence pattern that will leverage the open page, where open page will be better than closed page?
Most programs that have a lot of loops, right?
Perfect. Which means they have high locality, correct?
Yeah.
Yeah, which means by high locality, open row will be in fact a good thing because you have many hits. Perfect. What about closed row? Is there a sequence that you can imagine or a possible scenario of a program that you can imagine closed row will be better than open row?
For loop that access random addresses.
Random addresses, or you have something like pointer chasing, or you have linked lists that are distributed across your memory, right? That means now you don't have a lot of locality and it's better to have closed page. That's correct. Does someone know what our machines right now have? Open or closed? What do you think?
Open. I don't know, but I'm just guessing it should be open because our machine focus about increasing the average performance, not the worst case.
A good argument.
Worst case latency.
A good argument. Yeah, good argument. What others think? So we have open here for Salah. Like, is there any other preference?
I think
open because
have, yeah, sure, go on.
Mushfiqar is saying open. Perfect.
okay, yeah.
Okay, good. Mohammed?
I think they may have both. Like,
what do you mean by both? How you can have both?
Are you thinking about it? For example, it's a policy, right? At the end, so we can implement both of them, and like based on the program. I don't know. I was just thinking about it in this way. For example, if I assign CPUs to do, for example, the sequential accesses, and some CPUs to make the random accesses. So I will have like, okay, so the open policy will be better for these CPUs, and this closed policy will be better for these CPUs. That was my thinking, for example.
But at the end, you would end up having, it's a single controller, right?
Yeah, that's what I am trying to do, like two controllers, only one controller. Like we will have like two controllers here.
Okay.
Thinking about it that way. Yeah, I was thinking about it in that way.
Yeah, interesting. Yeah, that's also that's also good. One. Yeah, that's also a good argument. We will see right now that you're not too far from what's going on. But what others think? Is there anyone saying we might have closed page policy? Hello? Ryan? Teresa? John? What do you think?
I think probably open row.
Open row, good.
Yeah, for me, I would say open row just for the same argument as Salah.
Okay.
Because we're looking for performance. Okay. But I think Mohammed's argument makes sense that it could be a combination of both.
Yeah. Okay, so in fact, what we have is, okay, I would say almost all the answers are correct, right? The reason for this is what we have currently is something that is usually called as hybrid page policy, which employ most of the time open page because most of our applications are high locality applications. But the hybrid page has a counter that keeps counting how many row hits you would have, right? And I believe maybe one of the assigned papers in DRAMs might touch on that. But generally, the idea is the following. If I have a lot of hits during runtime, I would keep an open page, right? So normally I'm running an open page. But if it turns out that there is an application or a scenario that is causing a lot of conflicts, so my counter for the number of hits will go below a certain threshold, then you would switch to closed page. So it's kind of something, a dynamic policy that switches between closed and open. So we don't have both, Mohammed, but what you said is like close to the correct thing. It's a single policy, but you dynamically change it, right? Based on the behavior of the program.
Yeah, I see.
But we don't need to change the DRAM itself, right? Because this policy implemented in the controller side, right?
Yeah, that's correct. You don't need to change the DRAM because at the end you issue valid commands to the DRAM. So effectively, what is this open row or closed page? It's just issuing a pre-charge command or not issuing it after the request, right? So the way close page is implemented is you say for every request, it will be composed of 3 commands. You start by activating the row because the row is empty. You do the read write, and then at the end, before you leave, you pre-charge your own row. That's it. And this is called implicit pre-charge, which means it happens for every single request. But because it happens after the request, not before it, it's not in the request latency critical path, right? That's why we said the closed page policy has a better latency than the conflict, because in the conflict case, you need to start by the pre-charge, which means you need to wait longer until you get your data, right? In the other, in the closed page policy pre-charge, here you start by an activate or read or write, and once you issue the read or write, your data can start transferring in the same time that you issue the pre-charge. So the pre-charge is overlapped with the data transfer, so it's not in the critical path, right? But because each time you pre-charge the row, the coming request will find the row empty and it will not have a conflict. This is what is meant by closed row, is each time the row has to be closed, right? Good?
Yes, thank you.
I guess here we have something about the adaptive page policy that I discussed, which you need to predict whether or not the next access to the bank will be the same row, and based on this or based on the counter, you have an open row or close row. Here more discussion about open and close, which I believe we already covered enough. Good. So let's now switch. So maybe let's have a very brief break for 10 minutes, and then we can start at 3:30 for the other lecture, okay? Thanks, everyone. I'm still here if you guys have questions.
Dr. Mohammed, I think you are going to clarify the questions, the last question, right? About if I have 2 channels and how they access.
Yes. Salah, are you still here?
Yes, Professor.
Okay, so your question was if you have multiple channels, if it's completely independent, or you know what, maybe let me go back to the slides because they will help. Are you able to see the slides? Let me see. Are you guys able to see the slides?
Yes, doctor.
Yes.
Okay. So we were discussing multiple channels versus multiple. Oh, that's way far from. Let me see which part was that. Okay, so it's this slide, right? So I said you can have 2 possible scenarios. Oh, why did we exit the screen? Okay, so you can have 2 possible scenarios. The first one is you have 2 independent channels, but each one has its own memory controller. And in this case, both channels will be completely independent. They would have their own data bus, address bus, everything, right? So you don't need to worry about that. That's one option. But in fact, what we have in our machines is not that. What we have in our machine is that it's a single memory controller because you don't change the CPU. It's a single controller, but the controller will have a wider interface to be interfaced to different channels that are sharing the data bus. So what we have in our machines is that it's a single memory controller that share the data bus into different channels. Good. So the channels are completely independent except that they share the data bus. On the other hand, maybe there are systems where you have multiple controllers for example, in an FPGA or so. And then each controller has its own independent channel. That means these are completely separate systems. They are not even interfered. They don't see each other. They have different memory space, and they are completely independent, right? Here, they are logically independent, but they still share the data bus, right? And that's the main difference. And this is the fact, like this is in fact the scenario in our machines. Does this answer your question, Salah?
Yes, so for the first like architecture, it supports data sharing among different CPUs, but the other
Correct.
one, it seemed like a different computer or a different machine, like, or different node.
Or maybe even the same computer, but it just maps things in different ways. Like, for example, a program goes here while another program goes here, but they don't share data. So you are correct. There is no data sharing here.
Okay.
Good, thanks. So I will just, let's continue in our break and then come back in 5 minutes then.